Okay, this is a lesson on electrical potential. It's a little bit longer than the last lesson. It's a whole 6 slides. And you may see some similarities with gravitational potential, which we went through several weeks ago now. Okay, so what is electrical potential? The definition: electrical potential at a point in a field is the work done per unit charge in moving a positive test charge, positive is important, that's why it's bold, from infinity to that point in the field. Okay, so the equation for it is delta W, so the work done, is equal to Q, the charge, times delta V, which is the change in potential. An electric potential is defined as 0 at infinity, just like gravitational potential was. Electrical potential difference is the difference between difference in potential between 2 points. So when we talk about potential difference, when we're talking about electric circuits, that's what it is. Okay, if we have, in gravitational fields, when we looked at gravitational fields, all of the gravitational potential was negative. With electrical fields, because we've got attraction and repulsion, you've got to pay attention to the charges. So if the charge that we are moving towards or away from is positive, then we're going to have a positive electrical potential. If the charge is negative, then we're going to have a negative electrical potential. It's reasonably straightforward and easy to understand. Okay, just like with gravitational potential, we use the concept of equipotentials when we're looking at electrical fields. Equipotentials are lines that are drawn to show places with equal potential. And if we're moving something along an equipotential, we don't do any work. So in these diagrams, the equipotentials are shown as the dotted red lines. And you can see that going parallel to the plates in a uniform field or in circles around the charge in a radial field will be an equipotential. Okay, so the electrical potential in a radial field, we use the equation V equals 1 over 4 pi epsilon naught Q over R. And we've got all the definitions of what those terms are listed there for you. Remember, the unit of electrical potential is going to be volts or joules per coulomb. Okay, so if we compare that to our gravitational potential, you'll note that there is a minus sign in the gravitational potential equation that is not there in the electrical potential equation, and that's because gravity is always attractive. In the electric potential equation, we're always looking at the potential if we're looking at moving a positive charge. So if we've got a negative charge, it's attractive, and we take the negative from the Q. Okay, so graph of V against R, you need to be able to draw this, and fairly straightforward. It's a 1 on R relationship. Note that it's positive, so we're assuming it's around a positive charge. Then if we have a look at the graph of electric field strength against R, same deal, you have to be able to draw this 1 on R squared relationship, and you'll note that the change in potential is equal to the area under that ER graph. So what does that mean in terms of our VR graph? Well, that tells us that the gradient of our VR graph must be equal to the electric field strength. And that's exactly the same as it was when we were looking at gravitational fields. So that's it for this lesson. Have a go at the questions. Email me if you have any problems. Good luck.